In this video, we will discuss the paper published in KAI 20 titled From Data to Insights, a layered storytelling approach for multimodal learning analytics. Learning analytics was defined in 2011 as an emerging discipline focused on using learners' data to create a deeper understanding about learning with the purpose of optimizing it. Nowadays, several learning analytics products have taken the form of visualization and dashboards that have been deployed in a wide variety of environments. However, recent reviews have been highlighting serious limitations in most learning analytics systems. These include problems that the students are experiencing in terms of interpretation, sense-making, and acting upon their data representations. In this paper, we focus on an authentic learning situation in the context of clinical simulation, in which nurses develop and put into practice critical skills while looking after patient mannequins that need different kinds of clinical support. Simulations are often facilitated by a teacher supervising 5 or 6 groups at the same time. Our vision is to automatically capture traces of what's happening in these simulation classrooms using sensors to augment teachers' monitoring capabilities or provide feedback to students. In practice, these sensors generate different kinds of signals. For example, the physiological wristbands contain multiple sensors that generate heterogeneous data streams of electrodermal activity, blood volume, temperature, and wrist movement, which can be used to model constructs such as engagement or stress. Similarly, X and Y coordinates generated from localization sensors can be plotted into a floor plan, but more meaningful data can be obtained from system logs or observation applications in the form of actions performed by particular team members. A critical challenge is how to make sense of all these data and provide meaningful feedback in ways that students and teachers can actually understand, since they are not data experts. And most of them will end up being casual users of learning analytics interfaces anyway, especially students who are going to be interacting with an ecology of all their learning systems. The contribution of this paper is a layered storytelling approach to provide guidance to teachers and students while making sense of multimodal learning analytics interfaces. This model builds on a data modeling technique we presented at KAI last year called the multimodal matrix, which relies on knowledge from the domain to map from multimodal data to a data structure that has a higher order level of meaning. Let's look at an example. Let's say that we have interlocalization data, which contains X and Y coordinates by each team member in the classroom space. And to give these coordinates contextual meaning, we map each coordinate to meaningful areas around the patient mannequin, such as being at the bed head next to the patient, by the trolley, or at the bed footer. In each of these areas, nurses commonly perform specific actions. We transform the positioning data streams into a discrete data structure. We can do the same for other sensor data to convert data streams into salient aspects of communication, affective states, and clinical actions. Information contained in this matrix can be directly plotted, for example, as diagrams of the state of the position of each team member around the patient in relation to other sources of evidence. But this information is still not converted in feedback that nurses can actually make sense of for improving their own learning. For this, we propose to consider the notion of a learner model and teacher's assessment criteria to interrogate the multimodal matrix. This is, each teacher's pedagogical intention is mapped to particular sources of evidence that can be used to assess how students' activity is reflected that intention. For example, if one teacher's intention is that students effectively perform a cardiac resuscitation, multimodal data could be interrogated to assess whether students were at the right positions in the right time and performing compressions effectively. The final component involves the generation of data stories. To illustrate these data stories, we use a prototype we co-designed with teachers called the team timeline. This shows a series of actions detected by different sensors on a timeline for each team member. In this case, a team of 2 nurses. But this visualization is inviting students to explore the various data points. Previous studies show how students analyze point by point and use their own criteria to make sense of the information. As a result, we call this the vanilla timeline because it doesn't offer any guidance to students to interpret the meaning of the position of the actions, their timeliness, their correctness, and combinations of right, wrong actions. This is a visualization, but not a data story. We created two data storytelling prototypes. The first was co-designed and then tested with teachers for a simulation in which a patient has lost consciousness and stopped breathing. We enhanced the basic timeline with storytelling layers. For example, this one layer tells a story about the time responsiveness of two students executing clinical actions according to the basic life support protocol. We propose to automatically render visual elements on top of the vanilla visualization according to the learning intentions of the teacher. We translated each pedagogical intention into a set of rules to add visual enhancements, such as emphasizing relevant data points while sending others to the background, adding an explanatory title to communicate the main message of the story to the learner in plain text, shaded areas to group data points, as in this case, to represent slower responsiveness of the team in executing chest compressions to the patient, and annotations that explain the meaning of particular data points by highlighting events that were important, for example, a delay in delivering a resuscitation shock. Other layers can be added to highlight mistakes made by the team. For example, if the airway nurse was not physically located at the bedhead during the resuscitation, or showing arousal peaks automatically detected by the physiological sensors. Additionally, we also show the rules used to add the different elements in a particular layer, which were shown to teachers and students. We deployed a second prototype in an authentic classroom, which was shown to the students to facilitate a reflection after they perform a simulation that was part of their regular classes. In this case, simulations were about a patient who is reacting adversely to medication. We focused on the teacher's pedagogical intentions as well. For example, for this particular simulation, students had to assess the vital signs of the patient every 10 minutes. We enhanced the timeline that invites the students to explore all their data. Here is an example of a team of 4 nurses. Students had the option to select the different stories using the controls at the bottom of the interface. For example, regarding the first data story, students checked the vital signs of the patient initially, but failed to keep checking them frequently afterwards, which is explained by the interface using a combination of visual elements and narrative. The team administered the medication and immediately realized there was an adverse reaction and stopped it. But they forgot to perform an ECG, which is a recommended action after such a situation. This error by omission is highlighted in the interface and explained to students using text. We also show textual feedback about arousal levels automatically detected by an algorithm based on a student's electrodermal activity, inviting students to reflect on, for example, why the 4 nurses in this team experience increased arousal by the end of the simulation. We analyzed teachers' and students' reflections using the LabHead protocol, which gives us a series of preset themes of analysis in terms of the added value of the layers compared to the vanilla visualization, the envisaged classroom uses, the effect of the automated assessment of a student's accountability, and the impact of opening the algorithms used by the system. Most teachers and students were very optimistic about the idea of dividing the potential stories that can be told based on the data into layers to scaffold reflection. Teachers also appreciated the potential of augmenting the kind of evidence they could have at hand to provide feedback, including aspects that may be hard to see during the face-to-face activity. Some students also agreed that dividing the data into sections helped them make sense of the implications of their actions. By contrast, the vanilla timeline was proven more difficult to digest. Students also emphasized the potential of using the tool as a complement of the feedback that they commonly received by the teacher in the limited class time. Regarding the classroom use, Both teachers and students strongly highlighted the potential benefit of using the layer interface to augment teachers' capabilities in leading evidence-based in-class debriefings, or with suitable scaffolding, a personal reflection task assigned to students as homework. Another potential role of the interface is in the redesign of simulations, especially if teachers find recurrent pain points experienced by students during the simulations. In terms of accountability, teachers were a bit worried about how this information can be disclosed to students, especially because students could get uncomfortable in being put on the spot, especially if they made critical errors during the simulation. Two strategies were suggested to address this. The information could be kept strictly confidential, but this would mean other students would not be able to learn from others' experiences. Alternatively, the interface could be de-identified and shared with other students within the same classroom to avoid criticism. However, the students were surprisingly not uncomfortable at all. And all the students were really keen about sharing their data stories for others to learn from their experiences before they go to real clinical placements, especially if names are not disclosed. All teachers suggested that students could learn from opening the algorithm so they could compare their performance to the parameters expected according to national guidelines. In terms of manipulability of the rules, two educators suggested that rules parameters could be manipulated according to the level of experience of students, but other educators argued that rules should remain the same because even first-year students should be aware of what is expected from them once they graduate. By contrast, the students were less interested in the algorithm. Some suggested the benefit of understanding the expected parameters so they have a frame of reference, but they generally agree that they are not in the position to change these parameters since teachers are the ones who have the pedagogical expertise. These insights contribute to inform this growing interest in opening the black box of the algorithms to teachers and students to understand to what extent this can be actually useful from a pedagogical perspective. In summary, our findings demonstrated the potential of the layered storytelling approach in helping reduce the complexity of learning analytics interfaces. Instead of having an interface that invites to explore the data as analysts do, we can create learning analytics interfaces that can be used by people who are not necessarily trained in data science and data analysis. This has the potential to lead to deeper reflection based on objective data, especially for complex multimodal analytics of ephemeral and physical classroom activity. In the clinical context, our approach has the potential of helping teachers to revise the instructional design of the simulations and in creating context-specific analytics that can augment the feedback that can be provided for specific clinical scenarios. In our study, this was achieved by translating the pedagogical intentions of the teacher into visual feedback and annotations, providing reflective guidance for the specific learning task at hand. Evidently, our approach can also provoke discussion around the risk of bias for interfaces that automatically guide students or teachers to pay attention to specific data points. The risk of false negatives is important if certain errors are not captured. Students can end up focusing on mistakes that are not as critical as others. Although we envisage this tool to be used to support formative assessment, teachers also express both interest and concern in using the tool for summative assessment, as simulations are commonly used as safe environments in which mistakes are allowed and sometimes encouraged. Finally, ethical issues related to data ownership, sharing, and the identification of multimodal data were partly covered, but this is an area that deserves further exploration. Thank you very much for watching. We invite you to read the full paper to know more details about our studies and feel free to contact us. Thank you.